This is the 7th video in the series devoted to Bessey shuffle diagrams. Recall that a shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also, remember our color coding of the digits between 1 and 8. The positions 1, 4, 6, 7 are color-coded black, and the positions 2, 3, 5, 8 are color-coded red. This will help us keep track of what happens to the cards located in positions in set A relative to the cards in positions found in A complement, namely 2, 3, 5, 8. As a quick reminder, the notation here means that cards in positions 1, 4, 6, 7 stay within those positions after a particular shuffle is completed. Also, cards in positions 3, 2, 3, 5, 8 remain in those positions. If that happens, then we notate that outcome like this. On the other hand, if inversion occurs, what will happen is the cards originally in positions 1, 4, 6, 7 will be moved to positions 2, 3, 5, 8 in some assignment. If that happens, then inversion has occurred and is denoted by this. Finally, recall that the Bessey sequences of order 8 can be described as follows. Here we have the 8 position values listed above. The first Bessey sequence has the following form and is summarized here. The 1s are in positions 1, 4, 6, 7, and the 0s are in positions 2, 3, 5, 8. For the inversion of this Bessey sequence, we obtain this, and the relationship between the 0s and 1s simply get reversed. So now the 1s are in positions 2, 3, 5, 8, and the 0s are in positions 1, 4, 6, 7. Our first shuffle for today is on the top row, far left. It's called a judicious transpose with a special stacking of the pairs of cards. So we begin with our ordered packet of 1 through 8, and we perform the shuffle. And then we record what happens after the shuffle is completed. We'll describe that first in Cauchy's 2-line notation, and then we'll convert it to cycle notation. So a transpose always begins the same. You deal out pairs, a 1, 2, then deal out the next 2, deal out the next 2, and finally the last 2. Now the stacking here is going to be the 4th pile goes on top of the 2nd, the 3rd pile on top of the 1st, and then we will stack right on left. So remember, this is pile 1, 2, 3, 4. We also call this kind of stacking leapfrog stacking. So here is pile 4. It leaps over pile 3 and is set on top of pile 2. Pile 3 leaps over this little packet and lands on top of pile 1. From here, we're going to stack the right pile on top of the left. So what is the new ordering of the cards once we've completed that shuffle? It's the following: 8, 7, 4, 3, 6, 5, 2, 1. So in Cauchy's 2-line notation, we obtain the following. The bottom row will be 8, 7, 4, 3, 6, 5, 2, 1. Converting it to cycle notation, we obtain the following. 1 goes to 8, so we have an arrow from 1 to 8. 8 goes to 1, so it wraps around, completing that 2 cycle, also called a transposition. 2 goes to 7, so we have an arrow from 2 to 7. And then 7 returns back to 2, so it wraps back around. So we get a second transposition. 3 goes to 4, so we have an arrow from 3 to 4. And 4 gets sent back to 3, so that completes another 2 cycle, or in other words, another transposition. 5 goes to 6, so we have an arrow from 5 to 6, and then 6 gets sent back to 5. So we have our fourth and final transposition. If we color code the digits, we obtain the following. Remember, digits 1, 4, 6, 7 are color-coded black, and digits 2, 3, 5, 8 are color-coded red. So we see that black 1 goes to red 8, which gets sent back to black 1. Red 2 goes to black 7, which gets sent to red 2. Red 3 goes to black 4, which gets sent back to red 3. Red 5 gets sent to black 6, which gets sent back to red 5. So here we can see that each value gets sent to a value of the opposite color. When that happens, inversion occurs, which means there's a wholesale exchange of cards in these positions with cards in these positions here. So they trade places in some fashion. To illustrate inversion, let's go ahead and begin with our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So the claim is if we perform this shuffle, we will obtain an inversion of the original sequence. An inversion just means zeros and ones have switched places in some assignment. So let's go ahead and just perform this shuffle a second time. So you deal out little pairs. Now the stacking is a leapfrog stacking from right to left. So the fourth gets stacked on top of the second. The third gets stacked on top of the first. And now we're going to stack the right pile on top of the left. Well, what does that result in? Do we get the inversion of the original Bessey sequence? We do indeed. We get 0, 1, 1, 0, 1, 0, 0, 1. And interpreting the cycle notation of our permutation, we know that the cards that were originally in positions 1 and 8 switch places. The cards originally in positions 2 and 7 switch places. The same thing for positions 3 and 4 and 5 and 6. And that leads to the following Bessey shuffle diagram. So it's right here. So we know that 1 goes to 8 and 8 goes to 1. So there will be a double arrow between 1 and 8. There will be a double arrow between 2 and 7. And a double arrow between 3 and 4, and finally a double arrow between 5 and 6. And up here we've indicated that inversion has indeed occurred. And at the end of this video we will show an application that involves all 4 of our new shuffles today.